Hello, my name is Kenny Gorman. I'm co-founder and CEO at Aventador. Today we're going to go through writing an interactive streaming SQL and materialized view engine using Apache Flink. So let's just dive right in. In this talk, I'm going to go through a bunch of slides, and I'm also going to go through a bunch of examples. Since we're doing the online version of this, I think it'll be better if we just kind of actually lead you through some examples and kind of show it to you as well. So I'll be going back and forth and showing you the examples as we kind of go through. All right, so let's just get started here. Let's give you a little bit of background and motivations for why we did this, and you know, what was our motivation in building a SQL engine around Flink. So, you know, Aventador has offered a managed Flink runtime for a few years now, and so even today you can go on Aventador and you can run managed Flink jobs. You know, upload your jar, integrate with GitHub. Run your computations and projects directly on Aventador, and it's fully managed. And the state of the art really, you know, has been let's build Flink jobs in Java or Scala and use the data stream or dataset API, maybe the table APIs, and maybe additionally the SQL APIs to construct your jobs or your computations. And that's been this kind of the state of the art. But while that's very powerful and those APIs are awesome, the expertise and time isn't trivial, and investment isn't trivial when you're writing Flink jobs. In fact, you know, these use cases that Flink powers and streaming use cases are oftentimes some of the most important use cases in the business. And so the teams that are building these use cases are oftentimes swamped. And so there's a long line of, you know, Java or Scala projects that folks need to build, and they're kind of behind the gun getting stuff done. So that's kind of where SQL comes in. You know, our sense of things is that SQL is a great way to build streaming jobs and computations. And so let's just talk a little bit about that. So, you know, obviously structured query language is 30 years old or so. And it's massively useful for inspecting and reasoning about data. Many people know SQL. It's, you know, a skill set that a lot of people have from you know, database work throughout their careers. Everybody from Java programmers to data analysts to, you know, DBAs and engineers, everybody, you know, mostly knows SQL to some degree. You know, if you're not familiar, it's a declarative language. It allows you to just ask for the data you want to see. You can say, hey, give me this data between these date ranges or with this attribute or this predicate. And it's very easy to use. It's very logical to iterate on the questions you're asking and build a statement that gives you the answer you're looking for. In the streaming context, it's been extended to accommodate streaming. So things like date, time, constructs become more important. Things like window operators become more useful because streaming SQL is different than normal SQL. It's not similar in the sense where you would just run a cursor. You'd run a statement. It would open a cursor. It would iterate the results back to the calling application, whatever that might be, and then that cursor would complete and be done. Streaming SQL doesn't work that way. Streaming SQL is always running. It's running on a boundless set of tuples, and the results are being spooled or sent to some other location as they fit the criteria. So a little bit different context in which the running of the SQL and the runtime of SQL actually works, and we're going to show you a little bit of that today. But the net is it's an amazing way to work with streaming data. And so our sense of things at Aventador is that, you know, look, something like 80% of all workloads can probably be represented in SQL, and probably should be, because you can quickly and easily build them. You have a greater set of folks within your organization who can actually maintain those jobs or change it as your needs change. And so it's a much easier and more approachable thing to not only get started with, but also maintain. But there will always be sort of that last bit that folks want to use Java or Scala for, and that's cool. You know, we support both and we believe in both, and together they kind of make a great combination. All right, so let's talk about SQL Stream Builder and the Aventador platform and kind of how we've implemented things. I'm going to talk through 4 various components, and we're going to show a little bit of demo on each one of these and dive in a little bit deeper on each one of these as we go through. So we'll kind of just talk through these. So the first one is Console. It's an interactive SQL editor. It is a web-based program. It's written in Python and JavaScript that allows you to create and submit Flink-compatible SQL jobs. And we'll show you that in a bit. There is also the virtual table registry, which is the source that you read from and the sink that you put your results into. So a moment ago, I talked about, putting the data, the results from your query, that data into some place. Well, the sink is that place. Now, what's important is a source is the predicate in your query. So the from clause in your query when using the virtual table registry, and that includes a schema definition. So even though you may be putting relatively unstructured JSON into, some Kafka topic or something and wanting to read that, with SQL, it has to be strongly typed. We have to know the name of the column, so to speak, virtual column, and we have to know its data type. And that's just how SQL works. So that's an important piece of what the virtual table registry brings to the table. Next is what we call Squelio or SQL IO. Its job is to parse SQL in real time, to submit jobs when that parse succeeds, and to give user interactive feedback as they're building SQL statements. This is an important part of the puzzle because we feel pretty strongly that if you can't iterate on your SQL statement, you're not going to be successful with SQL. So you need to be able to iterate on it, look at your data, decide what the results are, and look at them, and then decide, hey, I need to have a different predicate or a different date range, or I'm looking for something else entirely, and be able to iterate on those statements in real time. And that's an important part of the experience when using SQL. And then lastly, there's what we call Snapper. So Squelio and Snapper are two bespoke components for our stack. Snapper is in charge of materialized view management. So we'll talk a little bit about materialized views here in a little bit, but materialized views are essentially the latest state of any data by key. So if you have a bus and you're measuring its temperature, that bus ID might be 100 and its temperature might be 250 degrees. The latest state of that IoT device or whatever that stream is by key, by that bus ID, is going to be represented in a materialized view. And I'm going to talk a little bit in detail about what those mean. That's a new feature to our platform, and it's pretty cool, and I'll just dive into it a little bit. All right, so let's talk about sources, virtual tables, and schema a little bit. So, like I said, we have a virtual table registry. It allows you to create schema for streams. This isn't an easy task because, obviously a lot of people put, whatever kind of data. If you're using JSON, it's very likely that you have a topic full of somewhat messy documents. How do I make sense of that, and how do I use that in SQL? If you're using something like Avro as for your schema, then obviously your schema will be in pretty good shape from that standpoint. But how do we integrate with that and be able to read that? I'll show you that in a sec. And for sources and sinks, we have capabilities for Kafka on the read and write side for the source and sink side, S3 on the sink side, Elastic on the sink side, and what we call webhooks, which is simply it's like you would expect for a webhook. It's a callback to some external service sending data to it. So if you have a listener for email messages or a alerting framework or whatever that might be, you can use webhooks to integrate with that. And then lastly, input transforms. So input transforms are unique to our platform. Input transforms sit between a Kafka topic and that rigid definition of the schema that has types. And it allows you to mutate that stream on message by message basis and transform the data into something that might make that schema a little bit easier to use. For instance, let's say you have data coming in that half the data is valid and half the data is something that's just garbage, like maybe you just don't care about it. An input transform could be created to throw away and ignore half that data, and that way you just get the data you're looking for. It allows you to maybe join foreign data sources. Maybe they're coming from a third-party vendor or something like that, and they're not in perfect shape. Maybe they're arrays without keys or something that's hard to read. You can use input transforms to fix all those things. So let's just go in. Each one of these things I'm going to dive in and do a demo. So let's just kind of talk through this here. All right. So what you're looking at is the Event-Door console. We talked about that. This is the SQL window where we'd enter in SQL. I'm going to go to virtual tables and just kind of show you what that looks like. So I'm going to go to authorizations here. This is going to be the example we use today. And here we have a virtual table. It's just a named authorizations. It's coming from Kafka, so it's a Kafka type source. And the topic is named authorizations as well. It's in JSON data format. We have a schema for it, so if I wanted to, let me just highlight the schema here, delete it, and just say okay, let's just detect that schema. It's going to go out and it's going to duck type. That schema is going to read sample a bunch of messages. It's going to infer those data types, and it's going to build a schema around it. So you can see that it inferred it from a data value here, and you've got a totally inferred schema. So In this case, we've got authorizations for like from a a point of sale device. So we've got the amount, we've got the card ID, the card, we've got the Latin long that it happened in, and we've got some notion of a user ID. So that's our simple example schema here. For transformations, we can put a piece of JavaScript code. What's kind of cool about our JavaScript engine is it allows you to, it's actually natural and based. It allows you, the JavaScript gets compiled down to actual Java bytecode and delivered out and run as Java on the Flink cluster. So in this case, like, let's show you an example here real quick from our docs. So this is what an input transform, like a simple one, looks like. In this case, let me just highlight it. In this case, we're actually parsing the record. We're taking the headers. We are looking for various keys we're interested in, and then we are building additional schema around it. For instance, the topic and partition the data came from, and in this case, data center as well. So, and then that schema comes out looking like, okay, we have data center as a string, partition as a string, topic as a string, and then the ID that came through, from the original payload. So that's what an input transform looks like. It's just a snippet of JavaScript, allows you to transform, and maybe, if we wanted to delete the data, we'd say, hey, if topic is of X, just delete it, or if partition is Y, delete it, or maybe we don't want to look at data centers in Europe or something. That would be an easy way to just ignore that data on input. You could also do it in SQL later. It just sort of depends what you need your schema to look like. All right, let's go back to the console here. So we have nothing in there for this example because it's just a simple example. And then you can also set various properties. Okay, so where would we start reading in Kafka? What consumer group? Maybe we want to give it a consumer group or any other property. You can give those there. So that is the source. Now on sync side, you can add a sync of various types: Kafka, S3, Elasticsearch, and Webhook. We've got more coming, and those are where the data is going to go. The output of that SQL query is going to go to that spot. All right, so that's the virtual table part of the platform. So that's sources and syncs and virtual tables. All right, so let's talk about actually running some SQL. So a couple things to note before I dive in and show it. Again, our goal was to create an interactive SQL interface. We want you to be able to, as a user, we wanted the user to be able to iterate and understand and get feedback from their job in real time. Obviously, with a messaging system, an event system, it's very hard to know what the schema is. So that we just talked about, how we handle the schema. It also handles feedback from Squelio. So if the data types aren't correct, if it doesn't parse, the SQL just doesn't parse, it's bad SQL. It'll let you know that in the logs, and I'll show that in a second. It's Python and Vue.js, as I talked about. And results are sampled back to the interface. This is an important point. In a continuous SQL design like we have, how do I see the results if they just never come? If it's a balanced set of tuples, how do I iterate on that data? How do I know what I'm seeing? And so we designed a piece here that allows the data to be sampled back to the interface. We actually store it in Kafka internally and use WebSockets to sample it back to the web interface. And it allows you to see a sample of that data that's coming through. So imagine you have a window into that stream. You're able to see what you're filtering or whatever you're grouping by as that's flowing through, and you get a sample of that data so you can make those decisions and change your query. All right. There's also the SQL engine itself, which is Squelio. That, like I said, parses incoming statements. It maps that to data sources and syncs, handles all the schema componentry, ultimately building POJOs and including those in the jar that's being sent out to Flink, and it's written in Java. All right, so let's just show running some SQL here, and I'll show you the feedback. So I'm going to go to my history. I'm going to go over to this piece of SQL here. So what I'm doing is I'm running, this is actually match recognize. So it's part of the complex event processing SQL component or SQL language for Flink. If you haven't used match recognize in the CEP portion of Flink, I highly recommend it. It's awesome. In this case, what I'm doing is I'm saying, hey, I'm looking for authorizations that are climbing in a very short window through 3 different stops: 0 to 1,000, 1,000, 2,000, and 2,000 above. And this is my my design for catching fraud. So I'm using the CEP framework for that. One thing to point out is this authorizations is a virtual table. That's the virtual table we talked about before, and has all the columns and the data types that I can reference. So event timestamp, lat long, all that stuff. An event timestamp is actually inferred from Kafka. So that's kind of a virtual column and a reserve word that comes through as part of anytime you actually attach to Kafka as your source. So, okay, so then we're going to run that SQL, get the right version here. I pick the right version of our software. I'm not using any sync, so I'm just going to spool this and let it show its results in the screen. I'm not putting the results to any sync right away. I have advanced settings here where I could set a restart strategy. If this was like a production job that had to restart, and it can retry, has a retry logic built in, or how many way parallel do I want to run it? In this case, I don't want to do any of those things. I'm just kind of showing you guys how it works. Okay, so I'm going to execute that statement. The first thing that happens is we start to see, let me just actually start the job here. So I've got a little Docker container that makes pretend fraud. So that's starting up over here. Cool. That's putting some data into Kafka. And let's just go through the log here, and we can kind of talk through how it looks. So first of all, my statement parsed OK, as it says right here. We use Avro internally for our schema. We validate based on the hash that's the schema, what the schema is and how it's working. And if the SQL statement matches it, it does. So that's all fine. Then it goes ahead and starts to run the query. And this is what it knows: the query, all the data types. Oh, there's some results. Hold on a sec. There we go. Runs the query, gets the table columns, sets the schema, and gives you feedback about what that schema, it knows the schema looks like, says it's not using a particular sync, and launches a job and starts waiting for messages. So that's like, if everything works great, that's how it looks. That's a successful job. That's a actual Flink job that's running on the cluster now. Very serverless in nature, and it's off to the races, and I'm starting to get results here. Okay, so I can just see that, hey, here's a whole bunch of fraud that's coming through, and I could put that in some sync. Maybe I want to put that into data warehouse or whatever. Now, if I want to, let's just stop that. And you can see it's sampling the data as I talked about. Let's just go, I'm going to use VI mode, 1G. And let's just say I typed something wrong. I say select. Like that. So I get some bad SQL there. Just going to show you how it works. I execute that job just like I did before, but it says failed, returned an error. It doesn't pass Calcite SQL parser. That step, so it doesn't work. Okay, that makes sense. I correct my spelling, but maybe maybe I'm looking for a column in a schema that doesn't exist, right? So that would be another problem that could. Maybe I'm looking for Kenny Gorman. That's a column that's not in there. Run that, and it's going to say column Kenny Gorman is not found in any table. So this is, looks a lot like you would expect a database to work. Stop this over here. And gives you that feedback instantly. So I can build queries, I can add predicates, I can kind of build up a statement from small to large and iterate on it and play with it until I know that it's good, and then maybe I pick a sync to send it to. Okay, so that's how the SQL engine works. Once the job is launched, you'll see that it launches it as a job and it's running, and you can stop it and start it, and it'll pick up where it left off, and all the things you kind of expect from Flink. Okay, so that is an example of the SQL engine. All right, so let's talk a little bit about materialized views, how that works and why that's important. So the components that are involved are Snapper. I introduced that a couple slides ago, and console. So Snapper handles changes to materialized views. So as those results are coming through, we're creating a persistent data store of those changes. We're saving them by key, and you're able to then look them up using a REST query from a RESTful endpoint. It understands the schema and manages the creation of the underlying data structures, indexing, and then all the insert, update, delete activity that's happening on your stream. And I'll show an example of that here in a second. And then so there's a console component too. That's how you actually define the REST queries against those streams. And actually ultimately it's going to be a JSON return result set. I'll show you that too. You can query by any key via the builder interface. So this is an important distinction from our solution. Some others out there have, they can query by key only, and only by primary key, like a key value store. In our case, we felt it was super important to be able to query by any predicate, just like you would a regular database. So we tried to expose those, and it's a hard problem in terms of indexing. How do you index every column? How do you know what to index? How do you do that in real time without causing a lot of bloat? And so we've made a bunch of interesting design choices to kind of make that happen. It also allows you to manage API keys. That's in development, should be out soon. Probably by the time you read this, that'll be out. And then it allows you to generate the policies for Snapper. How does Snapper behave? How does it keep the data? What is the retention policy and things like that? So let's go over and I'll show you that too. So let's go back to the query that we ran, the authorizations with the match recognize, right? Our fraud query. So we're going to use that query. And now what we're going to do is we're going to define a materialized view on it. And what it's sensed here is that in authorizations, you have a bunch of keys based on the virtual table. So the materialized view knows what those keys are, and we use that. You can pick a key. So in this case, we're going to pick card. So we're going to aggregate data and store data by card. That's our virtual primary key, if you will. 300 seconds is fine for retention. You can age data. You can make it 3 seconds or 30 or 99999 and save it for a really long time. It just sort of depends on your use case. How long do I want to keep those keys around? You can always recreate it on job start. So sometimes you want a fresh data store when you restart the job, and also you might need to ignore nulls. In this case, we don't have to worry about those two things. Okay, so we're just going to go ahead and add a query now. And this is actually the definition of the REST endpoint and how we actually query it. So let's just say here that we can just do auths, and let's just give it a description. All right, and we're going to add columns. In this case, I'm just going to select all the columns. I'm really interested in the lat and long, but we're just going to select them all. You can see I've got all the schema of the output is the output of the query, right? So these are all the columns that came from the query as the output of the query. We can add filters. So this is what I was talking about. You can add a predicate for any one of these columns. So let's say I wanted to say maybe where lat's not null or something like that. If there was nulls in that, something like that, and I can build a complex set of queries there with ands and ors and relative and just whatever logic you want there. But in this case we don't need it. So I'm just going to delete that. I'm just going to go ahead and save that change. All right, so now we have a REST endpoint. I'm just going to copy that address. It's called authorizations. And let's just start up our fraud job over here again. Oh, it's already running. Cool. And let's go back and now let's run that SQL. So let's execute that. And now we have a materialized view as capturing the results. And the log will tell you that. By the way, it also mentions the free slots remaining, the Flink ID, and some other information that I forgot to mention last time. So we can just see that. The job's launched. And we'll go over here and let's just pipe that through GQ. So nothing yet. That's an empty array. Let's just kind of wait for some results. Let's make sure we're getting some fraud over here. Yeah, so there's some fraud going by. We're processing that in real time. Sampling the data back to our sink here. And then, okay, so now we're getting results back from, in this case, I'm just using curl. So if you were creating some sort of application and you wanted to include those results in your application, it's super easy to, just specify, like maybe it's Ajax or something like that. Specify that as your data source, and then maybe plot lat or long on your map, that kind of thing. So makes, whether it's notebooks or you're using you're just writing an application, or you're sending the data to some other microservice or something like that, makes it super easy to consume and use data from streams inside your applications. So that's materialized views. One thing I did want to mention that I didn't talk about was also functions. So we have user-defined functions. User-defined functions are defined in JavaScript, just like the input transforms. In this case, let's see. Let's see. This one's timestamp from epoch. So it's just a little conversion routine to get the timestamp from or get epoch from a actual timestamp. And you can see it's written in JavaScript. Its output is a string. Super kind of easy logic here, and then we're just using a date operator in Java and JavaScript to get that done. So super easy to implement. They work on the fly. You don't have to recompile or rebuild. If you just create that and then use it in your SQL right off the bat. So you could say 2TS in any one of these queries here, and it would work. So that's that. All right, so let's go back here. So that's materialized views. All right, so let's talk a little bit about Flink itself and how we utilize Flink under the covers and what it does for us. Let me just stop my job here. All right. So first thing to note is, everything's a job. Everything that we're doing ultimately ends up being a job. Squelio, you saw that interface that helps you create interactively create SQL and then send it out to the runner. It allows you to know that your SQL is being parsed and you've got it correct before committing to actually running a job. Then once you run the job, it's a normal Flink job. It's scalable and it has the semantics of its recoverability is the same as you'd expect with Flink. So, Flink's great for that. Obviously, you hear a lot of talks probably today about state management and how that works in Flink. So I won't cover a ton of that, but ultimately, like if I'm pulling data from Kafka and it's reading from a particular offset in Kafka, and I've got a window operator running and I'm doing aggregation, if something fails during that aggregation, then, and let's say it's an hour aggregation, I don't want to have to reread an hour in order to recover my job. And so I don't have to with Flink. I can reread whatever the delta is between now and that end window state, and I'll be off and running, and the job will start over again. So that's super powerful and very fast. So fast recovery is a very good trait of Flink, and something that's why we chose Flink and why we like it so much. And then also scalability, right? So I showed you how you can run a job in parallel. Ultimately, it splits it up into a number of slots over a number of task managers, and that's the sort of the scaling vector for the how it runs. We do run in session mode, so there is a Flink cluster in the background that's running all these things. It has a number of task managers. It has a number of slots per task manager. It's configured with RocksDB as the backend data store, the state management data store. We run Flink 1.8. Ultimately, we'd like to get moving to the Blink Planner. Blink Planner, if you're not familiar, just adds a whole much more functionality to the SQL grammar in terms of like functions and operators and things. So it's just adding richness to the SQL grammar and allowing you more options in SQL. So that's great. Again, like I said, it's running like any other Flink job. We ultimately produce a jar. I told you how the schema gets produced to just a plain old Java object that gets included, and that's how we know the schema when the job runs. And we run on this is supposed to say Kubernetes. It says Kubernetes, so I'll just call it that from now on. We run on Kubernetes as our underlying framework for running jobs. We don't use a operator, a Kubernetes operator. We actually have our own framework that uses Postgres and some other components and microservices to coordinate job running and coordinate Kubernetes and how that whole framework works. That's kind of under the covers, and that's not normally exposed to the customer, but that's kind of our underlying framework. So in terms of runtime and scalability. So if you need to scale up, Kubernetes is the component that would actually control that from our standpoint. We run on Amazon, Azure, and GCS. On Amazon, we actually run our own Kubernetes cluster, probably move to their managed Kubernetes at some point. But today we don't do that. So really it allows you to build these complex and multi-stage pipelines. So just to kind of give you a feeling for the architecture, you can start off kind of consuming maybe some IoT device data into Kafka. Maybe you're joining with some other data source. Maybe you're joining with Redis. That's something else we have capabilities for. And then maybe you're sending to a couple different places. Maybe you're putting it back in Kafka where you further aggregate it and cleanse it, and then ultimately put it in S3 so you can pick it up with like Snowflake or BigQuery, something like that. Or maybe you're just maybe your data science team is training models from S3, and maybe they're just reading the data from the buckets in raw form, and they're training models that'll ultimately become production models or something. Or a very common pattern is to actually aggregate that data and then put it into a database. So I talked earlier about how state management matters, how why it's important to materialize views of data. up until a lot us and others have created materialized views, you really had to put it in a database. There's no other way to stick the data somewhere so that it could be easily consumed by applications. Ultimately, applications really want that picture of in time of state, and so that's why folks traditionally have used databases. The downside is databases are expensive, and if you put a lot of data into them, they can be relatively slow. So a common pattern is to aggregate that data ahead of time, and then put it grouped by month or day or week or whatever that might be into the database. So you're saving storage costs there, and you're also probably increasing your performance. But we believe in a lot of use cases, you don't even need to do that now with materialized views. You could just use a materialized view. You could, populate your notebook or your application, like maybe you're writing a JavaScript application, plotting those bus temperatures I talked about earlier. That would be super easy just to have like a front-end application, maybe an Ajax reading that REST endpoint and plotting the map maybe on Mapbox or something like that. So that's kind of how we see it fitting into the larger ecosystem using SQL or even Java. Some of these processors could be actually written in Java too, if that was important. So ultimately, we believe that streams of the database. We want you to be able to treat streams of data like a database. We want you to be able to iterate on your queries just like you did with a database beforehand. It feels interactive. You're able to iterate on your query, build it, and then finally decide, okay, that's the thing I actually need to see, and then you can go ahead and run it, and that becomes a production job like anything else. All right, thank you so much, and I think now we'll take a couple questions.